Welcome. This video is going to look at the rest of section 3 from chapter 4 of the Brown SL chemistry book. And section 3 is looking at the structure of covalent bonds and how this affects some of the properties of covalent compounds. So polar molecules may or may not arise when you have polar bonds. And remember, the polarity of a bond depends on the charge separation within the bond. So whether or not there's a positive end and a negative end to the bond. And that depends on the electronegativity of the two atoms. If one atom is more electronegative, it will have a greater attraction for that bonding pair, and that bonding pair will spend more time closer to that stronger atom. So then, how do we know if a molecule is polar or not? Well, it depends first on the presence of any polar bonds, and then it depends how those polar bonds are distributed or what the shape of the molecule is, whether those polar bonds cancel each other out or balance, or if they give a dipole, a positive and negative end to the molecule also. So some things to keep in mind. Nonpolar bonds always result in nonpolar molecules. You can't get a polar molecule without polar bonds. The second thing is if you have polar bonds with equal polarity, so it's the same atom, so you've got 3 hydrogens bonded to the nitrogen, or 4 fluorines bonded to the carbon, so that's what I mean by equal polarity. And if they're arranged symmetrically, then you will also get a nonpolar molecule. You're going to get a polar molecule when you either have polar bonds with unequal polarity, so for example, 2 hydrogens and 1 chlorine bonded to the nitrogen, or if they have equal or unequal polarity and they're arranged asymmetrically. Either of those cases can give you a polar molecule. And polar molecules are said to have a net dipole movement. In other words, there's a more positive end and a more negative end to the molecule. Another thing to throw in here and remind you of is this idea of resonance structures. Resonance occurs when a double bond can be located at more than one position in a molecule. So the situation is when you have a double bond between 2 atoms and you have a single bond between the same 2 atoms. How do you know where the single bond goes and where the double bond goes? And the answer is you don't, because it goes both places. For example, ozone, O3, it has a single and a double bond. If I just draw it here, like so. And what scientists have found is the double bond doesn't just stay in one place and the single bond in one place. Instead, both bonds have equal length and strength, and it's about equal to a 1.5 bond. So the second pair of electrons is now believed to be delocalized or able to move throughout the molecule. So that extra pair of electrons, or its second bond, isn't just here, and it doesn't even jump back and forth between the 2 places. It just spreads out across the molecule, and it gives the molecule greater stability. So the closest we can get to showing this idea is to draw both possibilities here. So I could draw it with the single bond on this side, show both what we call resonance structure, but knowing that the real structure is actually a resonance hybrid. It's a combination of these structures. So the second pair of electrons, again, doesn't actually rotate position, but spreads out across the molecule. And then a third type of structure to mention is this idea of giant molecular solids. They're also called network covalent structures or macromolecular structures. And no matter which name you go with, the idea is that these are very different covalent bonds. And in fact, they have some covalent character to them, and they also have a lot of ionic character to them. Most molecules have a defined structure and exist individually or independently from each other, like H2O. You have all these individual H2O molecules. They can be a solid, liquid, or gas, but they're individual molecules. But carbon and silicon, because they have those 4 bonding electrons and it takes about equal energy to gain or lose them, they tend to form a crystalline lattice where all 4 bonds are being used. And they really look much more like an ionic compound where the size can be limitless, but it's 4 carbon bonds to 4 other carbons. So it's still a covalent bond, but as I said, the properties are much more like ionic compounds. They have a higher melting point and boiling point because you actually have to break the covalent bond between them rather than just the intermolecular forces. They tend to be good conductors, or they can be good insulators. You can bring out either characteristic. and they tend to be very hard. Think diamonds here. So carbon has several allotropes, which we're going to look at on the next slide. Well, silicon dioxide or quartz is the most common giant covalent structure for silicon. So an allotrope is just different forms of the same element in the same state. So oxygen gas, O2, and ozone, O3, are allotropes of each other. Carbon has some common allotropes of graphite, diamond, fullerene, and graphene. So I put in a small piece of the chart from page 144, kind of describing the difference between these four allotropes. But there's a lot more information along with the properties and uses for each on page 144 that I encourage you to check out. Reasons for checking it out is especially the graphene and the Buckminster fullerene has led to this whole new field of being able to deal with atoms on the atomic level, one atom at a time, and manipulating it, building things one atom at a time. And it leads to lots of exciting ideas using materials like graphene and then graphone, which is just graphene with hydrogen in it. So if you've heard the term nanotechnology, that's what they're talking about, and it's these giant molecular structures that are making this new field possible.